Good evening. My name is Brittany Fink, and my partner is Roberto Sainz. And today we will be talking to you about our project, the analysis of a polymer electrolyte membrane fuel cell for passenger vehicle application. Our agenda entails the introduction, motivation, and key objectives, our background, benefits, drawbacks, our references, Appendix A, B, and C. We begin the hydrogen fuel cell as an electrochemical energy source. It can be more environmentally friendly compared to a fossil fuel. However, the problem is due to the burning of fossil fuel releases harmful chemical byproducts into the environment. Fossil fuels can also produce less energy per volume than a hydrogen fuel cell. Another key point to the hydrogen fuel cell is that there is a reduction in greenhouse gases that can help with reducing climate change. When picking the hydrogen fuel cell as a topic, we approach it with the motivation behind the topic, how it has higher energy to weight ratio, thus including the lithium-ion batteries, making vehicles easier to handle and produce with the least amount of wear as possible. A battery is easily interchangeable compared to the lithium-ion battery. Furthermore, a type of hydrogen fuel cell is a polymer electrolyte membrane fuel cell due to the abundance all over. We can even use a hydrogen fuel cell for space exploration. Our focus includes the analyzation of between a Tesla and a Toyota Mirai, including the cost analysis. We will determine the flow of the fuel and oxygen and the temperature that affects the fuel efficiency. We will be able to run a simulation in MATLAB for the theoretical fuel cell. Furthermore, we will be discussing the environmental impact, including its benefits and drawbacks. Thus, including our background, we see that fuel cells create electric power by electromechanically oxidizing a hydrogen fuel source, such as hydrogen and methane. If pure hydrogen gas is used, the only product of the chemical reaction is H2O. If a hydrocarbon compound is used, typically methane products of chemical reaction will be H2O and CO2. Hydrogen-based fuel contacts the anode and separates the cation H+ and negatively charged electrons. The electrons are removed from the reaction through an external circuit, while the cations are passed through the proton electrolyte membrane and rejoined with the electrons at the cathode to produce water. 5 types of fuel cells include the solid oxide, which has high temperature and a high output, molten carbonate, which is low power density and high efficiency, phosphoric acid, which is sulfur sensitivity, expensive catalyst, proton exchange membrane, low temp with a solid electrolyte, and this is the one that we will be focusing on today. We also have our alkaline, which is lower cost, and then the CO2. Some benefits is that it has no harmful emissions. Hydrogen fuel cells can be transported through our development gasoline fuel infrastructure. Hydrogen fuel cells are very durable. They are vastly abundant on our planet and solar system. They're efficient from 40 to 60% compared to combustion engines, which are only 30 to 35%, and can be congenerate system to produce electricity and heat. Overall, very environmentally friendly. However, some drawbacks are that because of newer technology, therefore it is currently very expensive, fewer resources currently offering hydrogen fuel, steam methane reforming to process hydrogen out of methane results in a large amount of greenhouse gases, primarily carbon monoxide and carbon dioxide. Fossil fuels are also used to produce hydrogen fuel, and the hydrogen gas is highly flammable in the event of catastrophic failure. Here we start with our chemical balance. A brief explanation of the chemical balance is that at the anode, the hydrogen's fuel protons and electrons split. The hydrogen's cation travels through the proton electrolyte membrane, while the electrons are transferred through a wire as electricity. At the cathode, the hydrogen cations react with the oxygen supply to produce water vapor as a byproduct. Here's our energy analysis. Before we can actually start the problem and begin, we need to start with some assumptions. Some assumptions that we have included are ideal gases, fluids are incompressible, fluids are inviscid and no external work, no friction or fouling in the system is abiotic, and system is at a steady state operation. For our theoretical analysis, fuel cells will be analyzing. We must define some variables first before we can start working on the problem. These variables will be described as we go along, but the important ones to note are the steady state conditions we are applying. That is the atmospheric temperature and pressure, as well as the steady state current density, or 1 milliamp per centimeter squared. We start by calculating the real voltage output of our PMFC. For those who did not recall what a PMFC stands for, it is a polymer electrolyte membrane fuel cell. The real voltage can be calculated by subtracting the voltage losses from the theoretical thermal voltage output. These equations will be described in the following slides. The theoretical thermal voltage output can be calculated by dividing the negative of Gibbs free energy difference by the number of electrons multiplied by Faraday's constant. Gibbs free energy difference is referenced through the textbook and is temperature dependent. This equation yielded a value of 1.184 potential volts, but to get the actual voltage, we must start subtracting the system's voltage losses. The first of the voltage losses is the activation voltage loss, or the activation over voltage. This is the energy used to prep the electrolyte for chemical reactions to occur. To solve for overvoltage, we'll be using the Butler-Volmer equation. This equation is a bit complex, but it will be simplified after considering the parameters of our theoretical fuel cell. The first parameter to address is that our alpha, since our alpha is equal to 0.5, the reaction is symmetrical. This means that forward and reverse currents are identical and only one side needs to be analyzed. The second condition is the steady state, meaning there is no change in the current density occurring. JSS is equal to J. This implies the equation below. The simplified Butler-Volmer equation can be solved easily. As you can see, the activation of overvoltage is temperature and current related. Higher operating temperatures and current densities will require a higher activation voltage loss. All variables are known or were given, and the final value of 0.355 V is calculated. The next voltage loss to calculate is to change the transportation losses across the membrane. This equation introduces a new variable, the area-specific resistance, or ASR ohmic. This variable can be calculated by dividing the membrane thickness by the membrane conductivity. Both values are given in the system parameters. This produces an ASR of 0.1 ohm centimeter squared. The last voltage loss to calculate is the voltage losses due to the reactant depletion in the catalyst. This equation is shown below. As you can see, there is an unknown variable for limiting current density, JL. The limiting current density can be solved using the following equation. There's another unknown variable being the effective diffusivity. The effective diffusivity can be solved with the following equation, which presents us with another unknown, the normal diffusivity. The normal diffusivity, or binary diffusion coefficient, can be calculated using the following equation. It is certainly a busy equation, but all variables are known. As you can see, the equation is dependent on the critical temperatures, pressure, and molecular weight. The pressures A and B are given by the equation for pairs of nonpolar gas. After plugging in all values, we get the binary diffusion coefficient of 0.788 centimeters squared per second. With our normal diffusivity known, we can plug it back into the effective diffusivity equation. The effective diffusivity is calculated by multiplying the nominal by the porosity of the membrane. This yields us as an effective diffusivity of 0.199 centimeters squared per second. With our effective diffusivity known, we can calculate our limiting current density. All factors have been used before except the bulk reactant concentration, CR, and electrode thickness. With these parameters plugged in, we yield a limiting current density of 5 amps per centimeter squared. Now that we know our limiting current density, we can now calculate the voltage losses due to the reactant depletion in the catalyst. In the equation C is the geometric concentration loss coefficient. After plugging in the values, we obtain a voltage loss of 2 times 10 to the negative 5 volts. Now that we have all our voltage losses calculated, we can return to the original equation to obtain the actual voltage of the fuel cell. After plugging in the voltages to the equation, we can get actual voltage of 0.829 volts. This also produces an electric efficiency of 70%. Here are our results. We obtained the electrical data for the fuel cell, including the real voltage, voltage efficiency, and current compared to the area of the battery cell. We still need to calculate the empathy balance as well and run MATLAB simulations. Here are our references that we used. Right now we have 11 references, and we will continue to grow those as we do more in-depth research. This is our Gantt chart. It shows at where we are in the project. The red means it has been completed, and blue is meaning that it is we are beginning onto the new stages of the next part. The final report will be due December 7th. And here we have Appendix B. And this is just a gathering of all our equations and how we wrote them down in a detailed format so you can see them all clearly written. And this is Appendix B continued. And here we have Appendix C. This is our video report checklist. And this concludes our presentation. Thank you.